In the previous lecture, we looked at the method that we can use for simple duct layouts for sizing and finding the pressure drop in the duct runs once we have sized the ducts. And the two methods that we looked at were the equal friction method and before that the velocity method. In this lecture we will go through an example in which we have been given a duct layout with certain information, and we will size that duct system and find out the pressure drops in the runs by using both the methods. And later on we will see if the results that we have got for a round duct, how they will be changed if I replace that round duct with a rectangular duct. So that is the first thing that we will do, that we solve that layout by using the velocity method, and then we will solve it by using the equal friction method. And in both these cases we will assume that the ducts are circular ducts. And after we have solved these two cases, then we will see how the results would change if I, for example, solve it by using the velocity method, but instead of a circular duct we have a rectangular duct. So in the problem we are told that it's a round duct system. We need to find out the index run. Remember, the index run is the run with the maximum pressure drop, and we have to first solve it by using the velocity method. And in the velocity method we need to make an assumption about the velocity in the main duct and in the branches, and that velocity we have been already told about in the problem statement, that in the main duct, which consists of segments 1 and 2, it is 5 meters per second, and in the branches segments 3, 4 and 5 the velocity will be kept at 3 meters per second. Then we will solve for the same layout by using the equal friction method, for which the pressure drop per unit length is again specified as 0.7 pascals per meter, because we will need the dynamic losses as well. So for that the loss coefficients are required, and for this layout the values of the loss coefficients are given to us. If you look at this layout, these are the diffusers that we have. So we have diffusers at 3 locations, and for each of the diffusers the pressure drop is given as 5 pascals. Then we have the loss coefficients for various fittings in the layout, and at the entrance it is 0.82. So this planum is just a part of the fan assembly, and that is where the air will enter the duct, and again that is where we have a source of minor loss or a dynamic loss. Then there are T's. So as the name implies, it's a section which resembles a T. So we can see a T over here. You can see this is a T over here, and you can see that there are two values. One is T branch, the other is T through. The way to interpret it is that if we look at the flow of air through this fitting, it goes from the main duct and then it goes into the branch. So that is T going into the T, and from the T into the branch. So when we move from segment 1 to segment 5, we will include the loss coefficient T branch. On the other hand, T through means that we simply go through the T from one segment into the next segment, that is from segment 1 to segment 2. So we have different loss coefficient depending on whether we are going through that fitting or from that fitting into a branch. Then we have a elbow, 90-degree elbow. So you can see there are 90-degree elbows at various places. One 90-degree elbow I've marked. Then there is another 90-degree elbow. So we have another 90-degree elbow, and finally I think a fourth one over here. So we've got four places in the layout where we have 90-degree elbows. Then there is also a 45-degree elbow for which the loss coefficient is 0.23. I will come to that. Before that, we have two more loss coefficients, Y branch and Y through. So Y connection is what you can see over here. I will again mark it out. If you look at this particular fitting, it has the shape of a Y, and again we will have two possibilities, that the flow goes from the Y and straight through. So if we move from segment 2 to segment 4, that will be Y through. On the other hand, if we move from segment 2 into the branch, that is Y branch. And now we can see the elbow, 45-degree elbow over here. So if you look at it, it is going to make a 45-degree angle. The air comes in this direction, and so it will be making a 45-degree angle over here. So the air is turned by an angle of 45 degrees over here. So if I just want to show, this is the angle that we are looking at. So the air is turned by an angle of 45 degrees. And this is how we can mark out the various sources of minor losses. Having done that, we will move on to the solution using the velocity method. And this time we can see that in the layout the segments have been marked by numbers. So we can do it by numbers or letters, and the dimensions that we require are given, that is the lengths of the various segments are given. I'll clear up this diagram and then we will start with the solution. You can see that segment 1, the straight length is 6 meters. Then when we move from segment 1 into this segment, that is 5, it again has a straight length of 1.5 meters plus 1.5 meters. And similarly for the other sections we are given the lengths. The first thing that we can do is to size the duct, and you can see also that the volume flow rates at the 3 diffusers or outlets is also given, and we can work out the total volume flow rate of air in various segments by using these values. So that means in segment 1 we must be supplying the total volume flow rate that is then distributed into the conditioned space through these 3 outlets. So you will sum up 0.071, 0.095 and 0.071 again, and the resultant flow rate will be the volume flow rate that will be delivered by the fan into segment 1. So when you move from segment 1 into segment 5, part of the air, that is 0.071 cubic meters per second, will go into this segment. The remaining will then be carried on forward to segment 2. So in segment 2 the volume flow rate will be the sum of these 3 minus 0.071. that means the sum of the other two values, 0.071 and 0.095. And then finally when we go into the other segments, over here the volume flow rate will be 0.071 in segment 3, in segment 4 it will be 0.095. We have already been told the velocities and the volume flow rates can be worked out. So once we have that, we can find out the area. Once you have the area, that is the cross-sectional area, and assuming it's a circular duct, you can find out the diameter. So that will complete the sizing part. And after that, we will need to find out the pressure drop through each of the runs. And it is convenient to draw a table in which we have these results, and that is shown over here, and all the steps are also mentioned over here. So the first thing that we can do, we have the segments, which could be numbers or could be letters. Then against each segment, because we have been given the velocities, we have entered the velocities. So we will fill up the second column first, or we can also fill up the first column. Because we are given the flow rates, we can simply add those flow rates and get the flow rate at various parts in the duct layout. And as I said, once we have got the velocities and volume flow rates, it's quite easy to find out the cross-sectional area of the duct, which is listed over here. Then that cross-sectional area is equal to pi d square by 4, which will give you the duct diameter in meters. So we have got the sizes for all the segments of the duct layout. So that is, the sizing is complete. The next thing that we need to do is to find out the pressure drops, and to do that we have to find out the frictional pressure drop and the dynamic losses. For the frictional pressure drop, you need the pressure drop per unit length for that segment, and then you will multiply it by the length of that segment to find out the total pressure drop that is due to friction. And to that pressure drop, then you will add any dynamic losses. Remember, dynamic losses is half rho v square, where v is the velocity, and multiplied by the loss coefficient, half rho v square into KL. And you can see that I have written down the pressure drops per unit length for each of the segments, and those are obtained from the friction chart. And we will go to the friction chart and confirm these values, which I've obtained and entered in this column in the table. And to do that, I will be using the volume flow rate and velocity. Keep in mind that in the friction chart, the volume flow rate is in liters per second. So all these values which are in cubic meters per second have to be multiplied by 1000. So it will be 237, 166, and so on when we use the table. And then we have the velocities for these segments given to us. So if we start with segment 1, we will have a volume flow rate of 237 liters per second, and the velocity will be 5 meters per second, against which I've shown that the pressure drop per unit length is 1.33. And we can see that. Now you can see that we have a volume flow rate of 237 liters per second. This is 200 over here. The next one is 300. So what I will need to do is to draw a line vertically upwards from the point where the volume flow rate is around 237. It is a logarithmic scale, so it's not a linear scale, and the values that I have entered over here in the table are properly calculated using a logarithmic scale. So we will go upwards, and we will stop where this line intersects the velocity, constant velocity line of 5 meters per second. And then we move horizontally to read the value of the frictional pressure drop per unit length. and you can see approximately this is around 1.3, and I will just mark this value over here that it is 1.33. over here. Then we move on to the next segment, segment 2. The volume flow rate is 166 liters per second. The velocity remains the same, 166. This is 100 and 166 is probably somewhere over here. And again we have to move to the 5 meters per second velocity line. As before, read the value of the friction factor. This time it has increased. It could be around 1.66, and the value I have taken is 1.55. The next is segment 3, and you can see before we actually find that value that segments 3 and 5 both have the same volume flow rate and the same velocity. So once we get the friction factor for segment 3, we will reuse it for segment 5. Segment 3 has a volume flow rate of 71 liters. So this is 50, 60, 71, more or less the same as 70, but this time the velocity is 3 meters per second. And the friction factor value I have taken is 0.78. So this is 0.7. This is the line above. This red line is 0.8. So 0.78 is quite reasonable. And then segment 4, volume flow rate is 95 liters per second. So this is 90, 95 will be quite close to the value for 100, and again the velocity is 3 meters per second. That will give us the final pressure drop per unit length that we need, because the next one is the same as the other one that we had obtained earlier. And this value, this is 0.5, this is 0.6. The value that I have taken is 0.65 over here. And we now have the desired pressure drops per unit length for the first 4 segments. For segment 5 it is the same as for segment 3. We will return back to the solution. With these values we have got the complete table. The only thing that was missing was the pressure drop per unit length. And we can now begin calculating the pressure drops in the various runs. If you look at this layout, the first run will consist of segments 1 and 5. So I will call it run 1 5. Then we can look at the next run, that will be run which will be made up of segments 1, 2 and 3. So I will call it run 1 2 3, and finally the third run will be run 1 2 4. And in each of these runs we have straight sections and there are sources of dynamic losses. If we look at just run 1, I will verbally first identify those sources of minor losses, and then we will move on to write the relevant mathematical expression using which we will calculate the pressure drops and the dynamic losses as well. The pressure drop for the straight part and the dynamic losses. When we start with segment 1, right at the beginning there will be a dynamic loss due to the entrance effect. Then we have the straight section. So for run 1 we will calculate the dynamic loss plus the frictional pressure drop due to the straight portion of segment 1. Then we will move into segment 5, and when we move into segment 5 we go from the T into the branch. So the dynamic loss will be T branch. Then you have a straight section for which we will have the frictional pressure drop. Then we have a 90-degree elbow, so there will be another 90-degree loss, dynamic loss. And then we have a straight section, so we have a frictional pressure drop due to that straight part of the duct. And finally there is a loss due to the outlet of 5 pascals. So that is how we will build up an equation, substitute the relevant values, and then find out the pressure drop for this particular run. And a similar exercise will be carried out for the other 2 runs. I will now move on to that equation that we have to start with. Make sure you first write the full algebraic equation and then substitute the numerical values. Okay, do not substitute the numerical values first. The algebraic values tells us how well you have understood the process for calculating these pressure drops, and even you might also have the advantage that some of those pressure drops might be again required. So if you have calculated them separately, you don't have to repeat those calculations again. For example, if you move to segment run 1 2 3, if you have the pressure drops for segment 1, when we have gone through the pressure drop for segment 1 to 5 or run 1 5, then when we go to run 1 2 3, the pressure drops for segment 1 will simply be the same as we had got them previously. Similarly, when we have done run 1 2 3 and we want to go to run 1 2 4, the segments 1 and 2 are common to both, and those values which you have already calculated will simply be inserted as it is to calculate the pressure drop in the run 1 2 4. Now let's move to the mathematical solution. Okay, you can see that for run 1 5, the total pressure drop is the sum of the frictional pressure drop in segment 1. The subscript 1 it tells us it's the frictional pressure drop in segment 1, and the pressure drop or the dynamic loss at the entrance. After that you move into segment 5, and in segment 5 the 2 straight portions of 1.5 meter length each can be combined into a single portion that is of length 3 meters, and then you can calculate the frictional pressure drop due to that straight part of the duct. Remember, now there were 2 sources of dynamic losses. One was when we went through the T into the branch, so that comes in first, and then we had a 90-degree elbow, and that is also shown, and finally the pressure drop at the outlet or the diffuser, that is delta P with a subscript DIFF for diffuser. Then the pressure drop can be calculated knowing the pressure drop per unit length, that is the frictional pressure drop delta P by L for segment 1 was 1.33. we know the length for segment 1, which is 6 meters, and those values you can first we have written down the algebraic equation, then in the next step you will see we have substituted those values. KL for entrance into half rho v square, and the in half rho v square the velocity v will be v1. You will use the velocity v5 when we calculate the dynamic losses in segment 5, and that will be all because we only have 2 segments. So when you move into a fitting and you want to calculate the dynamic loss, you will calculate the dynamic loss based on the velocity in the downstream segment. So you won't use v1 over here, you will use v5 to calculate the dynamic loss. And again we have the frictional pressure drop per unit length for segment 5, which was 1.55 multiplied by the length of segment 5, which was 3 meters, and then the dynamic loss can be calculated for both the fittings by adding up the loss coefficients of the fitting, because half rho v square, that term is common to both. So I have taken that and added the loss coefficients for the T into the branch and for the 90-degree elbow, and then finally the pressure drop of the diffuser. So separately we have got the 3 values. 5 is for the diffuser, 11.41 is the total pressure drop in segment 5, and 20.28 pascals is the pressure drop in the first segment, giving us a total pressure drop of 36.69 pascals in run 1.5. After that we will move on to run 1, 2, 3, and in run 1, 2, 3 segment 1 remains as it is, that is delta P1 plus delta P entrance. But when we go to segment 2, we go from the T through into 2. So you can see the dynamic loss will be based on the loss coefficient T through, and then of course the frictional pressure drop due to the 4.6 meter length of segment 2. Then we have another source of minor loss, that is Y going into the branch, and then there is a 45-degree elbow, after which there is also a 90-degree elbow, and the total length of the duct is of the segment is given as 8 meters. So that will give us the frictional pressure drop, that is delta P by L for segment 3 multiplied by the length of segment 3, and at the end of course we have the pressure drop across the diffuser. Once again we have the same form that I've shown over here in a similar manner, that we calculated or wrote down the expressions for calculating the various losses. We will have an expression like that for segments 2 and 3 as well. The value for segment 1 I have directly written as it is. For segment 2, the frictional pressure drop, the length multiplied by delta P by L, which was 1.55. Then we have the loss coefficient T through is 0.26, and then half rho v square, and remember the velocity that we are going to use will be, because we are talking about segment 2, the velocity is 5, so half rho v square over here. After that we move into segment 3. Again the total length was 8 meters. In segment 3 the pressure drop was 0.78 pascals per meter. So we have got that frictional pressure drop, and all the loss coefficients are summed up for segment 3, y into branch, then the 45-degree elbow and the 90-degree elbow. So you can see those three over here multiplied by half rho v square, and this time in segment 3 the velocity is 3 meters per second, to which at the end we have the pressure drop across the diffuser, giving us a total pressure drop of 48.54 pascals. And the lastly, run 1 to 4, and you can see that because we have already got the results for segments 1 and 2, of course we write down the entire algebraic equation, but the numerical values you don't have to calculate. We can directly insert those values for run for segment 1 20.28 and for segment 2 11.03. All you have to do is now work out the pressure drop across segment 4. And when we look at segment 4, the lengths of the segment lengths are given in parts, that is 1.5 plus 1.5 plus 1.5, that is 4.5 meters, and the pressure drop for segment 4 was 0.65 pascals per minute per meter. So we have got that frictional pressure drop. The minor losses y through, then you have one 90-degree elbow and then another 90-degree elbow. So we have got two 90-degree elbows, and the velocity again in segment 4 is 3 meters per second, and then finally the pressure drop across the diffuser. That gives us a total pressure drop of 44.42 pascals. All we have to do is now identify the index run, which is the run with the maximum pressure drop, that is evidently run number 1, 2, 3, and that run will have its damper fully open. In the other two runs, what we will have to do, we will have to provide dampering. That means we will have to partially close the damper such that the pressure drop across that run again becomes the same as the maximum pressure drop, that is 48.54 pascal. That means from 48.54 we subtract 36.69, and the resulting value is the pressure drop that the partially closed damper will produce. Similarly, for run number 1 to 4, subtract this 44.42 from 48.54. The resultant pressure drop will be provided by a partially closed damper. The same layout will now be solved by using the equal friction method, in which the pressure drop per unit length has already been specified as 0.7 pascals per minute. So that is what we do. We can again construct a table, and the first column will be that pressure drop, and now that pressure drop will be the same for all segments in the duct layout. So I filled up that value for all the 5 segments. The volume flow rates are going to be the same as before, because those are the required volume flow rates that are to be delivered through those 3 outlets. So those will not be altered. But this time the velocities will change, and when the velocities change, we will have a different cross-sectional area and a different duct diameter. Now how do we solve this? After having completed the first 2 columns, we will have to move to the friction chart, in which what you will do, the first thing you will do is to mark out the value of the pressure drop per unit length of 0.7, and that 0.7 value will be the same all throughout the duct layout. So you just have to draw a horizontal line. Then you look at the volume flow rate individually for each segment. At that particular volume flow rate, you will have the point where the pressure drop is 0.7, and at that point you will read the velocity from the friction chart. Once you have got the velocity, then again, because the area is the volume flow rate by velocity, you will get the cross-sectional area, which is equal to pi d square by 4. So you will get the diameter of the duct. So that will be the sizing. And once again, once you have done the sizing, you find out the pressure drops in each of the 3 runs. This time what will be different is that the velocities are different, and of course the frictional pressure drop is different, although it's same in all of the segments, but it is not the same as it was in the velocity method. So now let's just look at the values of the velocity that we have got over here for various segments, 3.9, 3.6, etc. And again I will go back to the friction chart and verify these values. You can see that I have already marked out the line on which the frictional loss per unit length is 0.7, and I start with the volume flow rates, which are, to start with, 237 liters per second, and this is 200, this is 300, and again I need to have a value of 237, approximately somewhere over here. And we can see that the velocity is just under this velocity line, which is for 4 meters per second. So this is 3, then 3.5, this is 4, and this is 5. And the value that I have in the table is 3.9. So even if you had 4 meters per second, that is acceptable. So this was a volume flow rate of 237 liters per second over here. And the next value is 166. And we again have to come back to the same value of 0.7 pascals per meter. This time the velocity is somewhat above 3.5 meters per second, just around what I have marked out is 3.6 in the table. Then the third volume flow rate is 71 liters per second. So that's over here. Yet again we have to come back to that same line of 0.71. So this was 71 liters per second. And now you can see the velocity is around 2.8 something, and we have got a value in the table of 2.85 meters per second, which just by visual by looking looks all right. And that value of 71 cubic meters per second will also be applicable to segment 5. So for segment 5 again the velocity will be the same as that for segment 3. That leaves us with the last segment for which we need the velocity, that is segment 4. The volume flow rate is 95 liters per second. Because it's a logarithmic scale, the values tend to bunch up at the farther end, so they are not linearly distributed. And now you can see that the velocity over here is above 3 meters per second. Over here this is 3.5, and we are somewhere around 3.2 3.25 or 3.2 meters per second. So that is what we have over here. You will have a line like this showing the velocity, and this is 3, this is probably 3.25 is over here, and if you draw it properly on the using the right scale, you might be closer to the 3.25 value, but again if you use a value of 3.2, that is acceptable. And now that completes our column for the velocity. The remaining calculation is straightforward. You find out the area, and based on that area you find out the diameter or the duct sizes for each of the 5 segments. Once again, once we have got that information, we proceed to find out the pressure drops in the runs and identify the index run. You will see that the algebraic equations will remain unchanged. Only the values that you use in those algebraic equations will change, and I've written down those values. I have not repeated all that process that we had done earlier because it's going to be along the same lines. But if you are going to solve a problem in the exam in which you are asked to find out, let's say, the duct sizes and pressure drops using one of the methods, do ensure that you write down the full algebraic equations and then insert the numerical values. So that is for segment 1. We have the total pressure drop of 11.68 meters. For segment 5 we have 10.29. so run 1.5 gives you a pressure drop of 26.97 pascals. Similarly, run 1, 2, 3, you will have the same pressure drop for segment 1. Then you have the pressure drop for segment 2, and then the pressure drop for segment 3, and of course we will also have the pressure drops across the diffusers in each of these 3 runs, giving us a total of 32.93 pascals of pressure drop in run 1, 2, 3. Run 1 to 4 gives you a total pressure drop of 31.15 pascals. As before, run 1, 2, 3 is the index run, but it is not necessary that if you solve a particular duct layout by these 2 methods, the index run remains the same in both cases. It is possible that the index run may be different in the 2 cases. So that is a simple duct layout that we have solved using the 2 methods, that is the velocity method and equal friction method. What I will just like to again introduce you to is that, let's say in this particular case we had a restriction on the height available for installing the ducts, and if that restriction was that we had a maximum height of 2 meters in which to install the ducts, there would be a problem, because if you look at the various duct sizes, in both cases we are exceeding that limit of 0.2 meters. So we could have then been asked to reconsider our decision to use a circular duct and instead go for a rectangular duct. And let's see how things would change if you are going to use a rectangular duct. What you will do is to use these results. Okay, the results that we have got for a circular duct that we are satisfying the conditions that we need to provide in terms of the pressure drop and the flow rates, etc. The only problem is that we do not have sufficient height to install a circular duct. So can we replace it with the circular duct with the rectangular duct such that our height restriction does not pose a problem? And that is something that I want to consider, and that's quite straightforward. I will say that consider using a so that is what we want to do. And what it means is that the diameter that we have, if I'm just talking about the velocity method, in the column for diameter we have the values 0.246, 0.206, 0.174. That diameter becomes the equivalent diameter. And that we know is 1.3 times AB raised to the power 0.625. So let's just raise it. So that shows it's an exponent, and then we divide it by A plus B exponent. So we have got that exponent. And D again was, I'll just write down that value. For the first segment it was point, so I've started with the segment with the maximum diameter. 0.246 is the value. So that is the equation that we will start with, and we will say that we want a rectangular duct which will give us the same results. So what should be the size of that rectangular duct, using an aspect ratio of 2:1. When we say aspect ratio of 2:1, it means A is twice B. So that is A, and what we mean by A and B, those values. We have A over here, and this is B. Now what we will do in this equation, where we have A, you will substitute 2B, so it will become 1.3 times 2B square raised to the power 0.625. then it will become 3B raised to the power 0.25, and then there is just one unknown, that is B, and that will give us the value of B, which will come out to be, you can verify it yourself later on, 0.161 meter. And once you have got the value of B, just multiply that value that you have obtained to give you the value of A. And you can see now this duct will fit into that restricted space that we have, because that upper limit was 0.2 meters, and now we have a height of 0.16 meters, and that will solve our problem. Remember what I had mentioned earlier, that if we replace a circular duct with a rectangular duct, it will give us we will end up with a higher cross-sectional area, and we will also end up with a larger surface area, and that can also be verified for comparison purposes. If we think if we have a circular duct, then the cross-sectional area, which is pi d square, we had already worked it out as 0.0474 square meters, and the surface area for that duct will be pi dl, assuming a unit length of 1 meter. The surface area will come out to be 0.773 in square meters. So if you multiply diameter 0.0474 by pi, that should give us the number that I've written out, 0.14. So the diameter was not 0.0474, 0.246. So 0.246 into pi gives us 0.773 square meters. And the same we can look at for a rectangular duct, and this time the cross-sectional area will be A into B, and that value you will see will be A is 0.323 into 0.161, gives us a value of 0.052 square meters, and the surface area will be the perimeter times the length. We will assume again a unit length, so twice A plus B, that is 0.161 plus 0.323, that gives us a value of 0.968 square meters. So that is, we are using more material compared to the case of a circular duct, but because we had a restriction, we had to make that compromise. Okay. And of course, when you insulate the duct, you will also, because the surface area is greater, you will require a larger amount of insulation. The rectangular duct of course has the also merit that you can fabricate it on site, whereas circular ducts are not fabricated on site. You have to fabricate them off site and then bring on and assemble them at site. We will continue with this topic of duct design in the next lecture, and I will try to give you a brief idea of the static regain method as well, in a very simplified manner, although we won't be primarily be using that, but again you should have a fundamental understanding of that idea, of that method, and that is something we will take up in the next lecture.